Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to talk about the difference between the definite and indefinite integral, as well as talk about the net change theorem. So up to this point, we've been talking about the definite integral. And the definite integral is when we are taking an integral with a specific interval. So we have a lower bound and an upper bound. The indefinite integral is when we're taking an integral, but we don't have those bounds. And in this situation, all that really means is we're looking for the antiderivative. In fact, it's exactly synonymous with the antiderivative. So typically, when people say the integral of a function, what they actually mean is the indefinite integral, and what they're really talking about is the antiderivative. In fact, we use the terms indefinite integral and antiderivative effectively interchangeably. So a very important thing to note here is that the definite integral is a numeric value, whereas the indefinite integral is a family of functions, because when you take the indefinite integral, you're not finding one function, because remember, this is an antiderivative. And just like when we looked at antiderivatives, you're going to find a function plus some constant, because this could be any vertical transformation of that function, and without additional information, you can't fix in which version of the function it is. So we're going to look at that a little bit more in a moment. But one thing that's very important is this is a result of part 2 of the fundamental theorem of calculus. This is very different from part 1. So you might find some debates online and places where people talk about particulars of whether or not the derivative is the integral, the antiderivative, and which terms we should be using. So I just want to go ahead and allay a little bit of issues with this and let you know that if you hear the term integral and there are no bounds given, this is effectively the same thing as saying antiderivative or indefinite integral. If you do not give any bounds, this is what you're talking about: the family of functions. You are not talking about the numeric value. If there are no bounds, that's what it is. And there has to be some c in addition to all of the things we talked about with the antiderivative. However, if you do have bounds, including part 1 of the fundamental theorem of calculus, where we had an a and then an x, that was not looking for an antiderivative. That was finding a derivative, because we were taking the derivative of the antiderivative, which got us back to the original function. That was simply showing how the two of them were inverses, okay? So be careful of that when you're talking about part 1 of the fundamental theorem of calculus and part 2 of the fundamental theorem of calculus. So a thing that we wanted to go ahead and look at here is how we can use this notation in place of this capital F, which sometimes can get a little bit confusing when we're mixing up the capital letters and the lowercase letters, which is the reason why people will often default to this, and the reason why they'll say the integral of the function when they're talking about the antiderivatives. 90% of this is just a review of the antiderivatives that we've already talked about. In fact, there's a couple missing here that we talked about last time, like, for example, natural log isn't here, neither is e. If you want those, drop into the comments, I'll go ahead and put them there. A couple of things that I want to point out here is that one of the reasons we talk about them this way is that you can see how this works as a nice kind of operative way to write this. We use the integral as an operator, just like we used the derivative earlier. And then also, we take this, we call this the integrand. So we integrate the integrand to get the antiderivative. And so we would generally just call this the integral, right? And so we say that this is the integral of that, and that's why we use that term, the indefinite integral or the integral, interchangeably with antiderivative, because of this kind of setup. Now, a couple of things I want to point out that are very important here is that this plus c does a lot of work. It carries a lot of the weight of us not having to write in the interval where these antiderivatives don't exist. Like, for example, tan x has a whole lot of asymptotes. Everywhere that would be some version of pi over 4, or 3 pi over 4. No, yeah, yes, 3 pi over 4. This doesn't exist, right? Positive 90 or 270, right? You get an asymptote. And you'd have to put that in everywhere for that. You have to put a piecewise function. Same thing if you ended up getting an antiderivative of 1 over x squared. That's negative 1 over x. Well, that's annoying to have to put that in as saying where it doesn't exist, where the asymptote is. So we simply write the antiderivative with the understanding that it only exists on the domain where it is, and that if you have an antiderivative that might have a positive and a negative, like for example, if it has an absolute value built into it, like the natural log, then you're going to have to check that. That's simply understood to be baked into the entire idea of this uncertainty of the plus c. Okay, so know that that's there, understand that that's there, and be ready to check that. It's not typically something that gets thrown at students, but every now and then you get a test writer or you get a professor or a teacher who just loves to throw that at students as a gotcha. So just be ready for it and understand that it's there. Every textbook lists it and indicates it, but for some reason a lot of students just seem to ignore that we mention that every time it's there. The other thing, the very important note here is that if you are unsure when you take your antiderivative that you've created the right thing, it's very easy to check. Just take the derivative of the thing you made, right? So, for example, when you do cosine and sine, it's very easy to forget when you need to put the negative. Just check it, you know? If you take the antiderivative of sine, this one's really easy to forget that you need to put the negative because we're used to the fact that when you take the derivative of sine, it just becomes cosine. So when you take the antiderivative, it's easy to go, oh, well, that'll just become cosine. It's like, no, 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 because remember, the derivative of cosine is negative sine, which is the reason why the antiderivative of sine is negative cosine. Because if I take the derivative of this would become negative sine, so that negative is how this becomes positive, right? And so it's just really easy to forget that. So if you're worried about it, just check it real fast. Take the derivative, see what you get, okay? So this list is just kind of a helpful one. It is by no means exhaustive. And ultimately, just like I said with the antiderivatives, you are much, much better off to simply learn to work your way through them by remembering your properties, remembering your rules, and then kind of working your way backward, thinking, how would I get to this from a function, or what would I do? Now, there are also going to be some techniques that we're going to be learning in the next video that will help you with a lot more of the complicated ones. But just remember all of your basics. Remember your substitution stuff. Remember all of your basic algebra stuff. Try to simplify your functions when you can, and use your properties that you have up here. If you have constants, take them out and simplify your functions. If it looks like you have things that are being added or subtracted, break them apart. Remember, your integrals are distributable across addition and subtraction. So use all of those kind of things you've got and simplify stuff so that you're not having to work with big chunky functions when you don't have to, okay? So this is the net change theorem, and I'm going to be honest with you, I don't really know why it's in every textbook and why it exists. It is simply an application of the second part of the fundamental theorem of calculus, and also it's the entire reason why we introduced integrals in the first place. This is exactly where everything started. So I guess maybe that's the reason, is it's just bringing it full circle and saying, hey, fundamental theorem of calculus, Riemann sums, look, this is what we wanted to do to begin with. So yeah, we're just going to go ahead and apply an integral to exactly the same kind of problem we started with, which is that we have something like a velocity and we wanted to find a distance. You can also do this with something like if you have, say, profits, you're looking at sales and you're trying to figure out profits versus revenues, right? Now, an important note here is that this is called the net change theorem because you will get net change. Because as we talked about at the very beginning when we were talking about Riemann sums and when we first talked about the integral, it does take into account positive and negative automatically. So if you have a positive function part of your function and a negative part of your function, it will take into account that change and spit out the net total, right? So if you need to have the actual total change instead, you'll need to use absolute value. And a really good example of this is the difference between distance and displacement. Distance is the total amount of movement done. Displacement is just the difference between the beginning and the end. So for example, if something moves like in a circular pattern, then if it starts and moves in a full circle and stops where it started, the displacement would be 0. But the distance traveled would be that full arc length of the circle. Okay? So if we look at our example of the particle here, I didn't get to the full answers because you should be able to calculate those at this point. But I did get to the point to show the difference between the displacement and the distance. Over here, we took just the derivative, or just the integral of the basic function from 0 to 4. But over here, we actually had to break it up because we used the absolute value. And our function is actually negative from 0 to 3. So we had to use the negative function at that point. And then from 3 to 4, we had to use the other function. And we can break this up just using our integral properties. Okay, so knowing that our absolute value is a piecewise function, and knowing our integral properties, we break it up, and then we solve it. So if you are a little bit weak still on doing absolute value stuff, again, drop into the comments, join us on Discord, we'll help you out with that. So I'm going to give you a couple of problems to try out on your own, and then that's it for today. So I hope that overview of integrals helped you out, as well as that discussion about how we use the integral to discuss the change of a function. If you have any questions, feel free to drop into the comments or join us on Discord. And as usual, the answers to the exercises will be after this outro.